Hi, welcome to the Quant Zone. Today we're going to talk about a problem called Markovian magic on two dice rolls. So this problem is similar to what we did in the last one, but the approach is going to be very different. And the purpose of doing this problem is basically to help you illustrate how you can do the same problem using probability theory and also through Markovian chains. And we've discussed both of these theories in the previous videos. And if you've not seen those videos, I would highly encourage you to watch them before you watch this video. And the link is going to be in the description below, so please do check them out. And before we proceed in further and get into solving this problem, if you're not so far, please do subscribe to my channel and stay tuned for more videos coming up on the channel and the playlist, which is called the Spring Teasers. Okay, so in this problem again, we're talking about two fair dices, and in any throw, we're going to be throwing these two dices together. Okay, we care about the sum of the numbers that appear on these two dices. Okay, and again, basically in the setup, we have two players A and B, and player A bets that a sum of 12 is going to appear first, and player B says they're going to see two sums of 7 appearing on two consecutive dice rolls. All right, so there are two consecutive dice rolls. All right, so let's see how we can do this problem through Markovian chains. Okay, so in this video, like we mentioned, we're going to be doing the same problem, but this is basically I call it Markovian magic on two dice rolls. Again, similar setup, two players. They're two dices, standard 6-face dices. They're fair, so probability of each number coming up on the dice is going to be 1 by 6. Two players, again, A and B. A bets on some 12 will appear first, and the B bets that two consecutive 7 will appear first, okay? So, in the last video, we did this question by conditional probability approach, or probability approach in general. Now, this time we want to solve this using a smarter method, which is Markovian, chains. And this is the whole purpose of I was teaching all these complicated concepts so you can understand what this Markovian chain could do. So, if you've not seen the last video, I highly encourage you, basically, you have a look at that, and I've shared the link in the description. And the reason is because I'm going to be using some of these structure that we had used in the last video as a foundation to basically proceed in this problem. So again, if you remember that we had talked about the importance of first trial, the importance of the first roll of two dices. And we had represented the sum of the two dices by a variable called f. Okay, and we had said, look, f matters only to us if it's 7 or it's 12, or if it's anything else, it doesn't really matter because it brings us to the starting point of the game. And again, this is something very important which I wanted to mention again, because let's say if you got a 7 and let's say you got another number say 4, now player A doesn't win, and it chances of player A winning doesn't matter. It doesn't get influenced at all because player A needs a sum of 12, in the dice roll, and should appear first. And the second is basically the player B is only gonna win if they get a consecutive 7. Okay, and now even if they get the 7, it doesn't matter because we don't have a consecutive 7. We have a number 4 sitting in between. Okay, so it's essentially like a starting point, because you still have to get two 7s here, and for B, this is for B, and for A they have to get a 12. If they get a 12 in the next one, you're done. Player A wins. Okay, and again, if you still could not understand that, I would encourage you to again watch the last video. The link is in the description. I've talked in more detail of why this is important, and so we, this matters only if it's 7 or 12. Otherwise, basically, we are in starting state. Okay. Now, in Markov chain, when you were doing the Markov chain problems, or you're approaching the problems via Markov chains, the most important thing is basically forming this state space, or modeling the problem in a way that basically gets modeled well into state space. Okay. So here I say the states are, they're 7, they're 12. They are 7-7. That is basically when player B wins, and it's something called as what I call start. Okay, I can represent it as S in short. Okay, now let's see what I mean to say. So let's say this is the starting state S, and this is where we were, right? First dice roll could take you to 7. It's possible to reach the state, right? The sum of 7 sum of the basically numbers appearing in the two dice in the first roll is 7. It's possible. It could also be possible we get to 12. Yeah, it's possible. Okay, and it's also possible that we get to any other number, which essentially brings us to the starting state, right? So it can come back to itself as well. So I have covered all the three possibilities for this state right now. Okay, first possibility, we get a sum of 7. Second possibility, we get a sum of 12. Third possibility, we get nothing. We basically come back to starting point. Okay, now let's talk about this state number 7. Now from state 7, you could go to something, what I call a 7-7. That is, in the second roll, you get another 7, and here's where player B wins. Because player B, as you may recognize, that they bet on 2 consecutive 7 appearing first. Okay, so now if they win, well, that's great. Let's see what are the other possibilities from this state, because we're going state by state. So if you just want to cover all possibility for this one, right? So yes, you can reach 7-7. What is the other possibility? Can you reach 12? Yeah, sure. After the first roll, it is possible the second roll it comes to 12. So it's possible to reach state 12. Okay. Is it also possible to reach the starting state? That is basically after 7, you get anything else which is not 7 or 12. It's possible. You get, let's say you get 5, right? So you come back to starting state. This is also possible. So I've noted this last arrow here that tells that, hey, you can also come back here. Okay, now let's talk about this state 12. Okay, so I'm talking about this one right here. Now, if you remember this, the bet person A made is they get sum of 12 appearing first. Okay, and here what I mean to say is, if let us say, they somehow managed to get to 12, and it could be possible they went from here directly to here. That's the first roll was 12. It could be possible they went here, they got the first roll as 7, and then they came back. The next roll, say, was 5, so back to their starting state. And then they come back to 12. It is also possible. That's okay. It is also possible, they may do multiple rounds like this. It is also possible it can be basically you keep getting sum which is neither 7 or 12. So it could be just, hovering in this state from time to time. So you see, as I say, the number of rolls or the number of times you're rolling these dice is changing. Go back to those Markovian chain concepts we talked about. You're essentially moving one time step. So it's possible that x0 is here. So x0 is basically here. And x0 and x1 is also here because let's say you got a sum of 3, something like that. Okay, but anyways, it's also possible basically you go from here and you go here, right? So this is 7 and the 12 outcome here, okay? So from 7, we have covered all possibilities. We have covered the starting state, we have covered this state, and we have covered this state as well, okay? All right, now let's talk about state 12. So in state 12, the bet player A made was they get a 12, and they essentially got a 12, right? So they have won the game. From this state is nowhere possible to go because player A has won. And I can say the probability that if you reach state 12 and you're going to stay there is actually 1 because it's an absorption state. Again, you have to understand this was the bet which player A made, and they have been successful. Why? Because they reached this point here. That's only possibility. That's how you can only reach the state. Okay, so if you're thinking it's also possible to reach 7-7 before that, well, for that you may have to go here, and we will talk about this state, and then you will be able to understand why this model is actually represented correctly. Okay, so now as soon as you reach state 12, that means player A has won, and you cannot leave the state because the game is over. Okay, so this is absorption state. The probability the person stays in state 12 is going to be 1 once it reaches it. Okay, so state 12 is covered. Now let's go to state 7-7. So again, here what has happened is there have been 2 consecutive 7s that have appeared. Okay, and again, this is precisely the bet which player B had made. 2 consecutive 7s, sum of 7s will appear. Okay, so again, here the absorption, it's going to happen, and the player B has won. Game is over. You cannot go back to this state where only 1 7 has appeared because 2 consecutive 7 have appeared. Game is over. You cannot go back to 12. Why? Because if you reach the state, right, and you've not reached the state before, well, you can only reach the state or this state at first, right? So let's say if I reach the state here in 12, then I cannot get out. It's an absorption state, right? Similarly, if I reach, let's say, state 7, let's say somehow, this is one of the paths. If I reached it here, then I cannot get out. That means player B has won, okay? So this is a modeling of how we do Markov chains. And essentially what you would see is outcome of the game, winning or losses, either win or a loss, is going to be represented by an absorption state, okay? Okay, so now let's try to compute the other probabilities, okay? So I know we've added the numbers and the arrow, and I'll just quickly change the color to make it more aberrant. Okay, so I've added the probabilities for these 2 absorption states, but let's now also add the probabilities for the starting state. So what is probability of what we could also do is we could do this via transition matrix. So let's say we apply a transition matrix. Transition matrix is state J. So this is S, this is 7, this is 12, this is 7, 7. And this is I, which is S, 7, 12, 7, 7. Okay, so let's now understand what this number is going to be. So probability of SS, that means if you were in starting state, what is the probability that you still stay in the starting stage? Okay, what that basically means is game is starting, all right, and you roll a number, you roll basically the dice that the sum is neither 7 or 12. So that basically means is F, again, I think we've represented F already. So I'm just going to quickly go back and use the blue color. Okay, so this basically means is F is neither 7 or 12. Okay, the probability of this. And if you remember, this is going to be 29 by 36 because the probability that F is equal to 7 is 6 by 36. And the probability F is equal to 12 is 1 by 36. Again, refer to the last video where we did this analysis. Okay. And if you've not checked it out, again, it's going to be in the description. Okay, so similarly, this is already computed. So I can quickly say this is 29 by 36. Let me change the color here. 29 by 36. Okay, now what is the probability that it goes from S to 7? So what that basically means is the first roll, is a 7. So this is nothing but this. This is 6 by 36. Okay, then what's the probability? It goes from S to 12. And again, this is 1 by 36. Oops. 1 by 36. Okay. Now what's the probability it goes from S to 7, 7? Let's quickly go to the transition graph and understand what we're saying. So let me just quickly say, so from S to S, this is represented by this part of the transition matrix. So S to S, this is 29 by 36. So we can write it here, 29 by 36. Okay. From S to 7, 6 by 36. Again, this is represented by the first row being here. From S to 12, this is 1 by 36. Okay. Now what you see is from S, from the starting state, these are the three possibilities it can lead to: here, here, or here. Okay. Now you may see there's another column here, another entry here, which is 7, 7. Can you reach from S to 7, 7 directly? So what would happen if that were to be true is basically you're saying in one throw we got two consecutive sum of 7. That is basically you say you got two throws outcome in one throw, which is practically impossible, right? So that's why there's no error in fact going from here to here. And when there's no error going in transition graph, again from the last lecture, you would see that the answer is going to be 0. It's not possible. Okay. Now let's talk about state 7. So state 7 is, so the first one is probability from 7 to S. So this is nothing but probability you go back here. So from 7, again, anytime you roll a die, it's an independent call, okay? And probability of going to start state is same as saying probability of getting something which is not 7 or 12, right? Because again, if it was a 7, if it was another 7, you would reach here. If it was a 12, you would reach here. But if it's anything else, you're here, right? And for the dice rolls are independent, so we can easily say the probability is going to be this one. It's going to be 29 by 36, right? So 29 by 36 again. And I'm going to quickly write this here as well. It's 29 by 36. Okay. What's the probability you get a 12 in the next roll? Again, the dice rolls are independent, so it's going to be the same as an unconditional probability of getting a sum of 12. And okay, let me just do this here. So it's 1 by 36. And now you also see there's another entry, which is what is the probability that you get a 7? That basically means what is the probability you stay in the same state? Well, if you roll a die after this, right, that's basically a representation of time. The next time, if basically you roll a die, either you get another 7, either you get a 12, or you get anything which is other than 7 or 12, which basically puts you back in the starting stage. You can't be in the same state here, right? Because you have to record the sum of the dice which you get, right? So therefore, there's no arrow coming from here to here, and hence, the answer to this one here is going to be 0. Okay, so now I think I may have to realign this a bit. Okay, so what is the probability now from going from 7 to 7, 7? This is this one. So this is, again, we're rolling another dice and we want to find out the probability of getting a 7 on the second roll. Again, independent outcome. So this got to be the same as here. 6 by 36. And you know, when you're writing this transition matrix or transition graph, you also, I think it's good to write both because you can cover all the possible cases. And one sanity check is that everything here should add up to 1 in each of these rows. So 29 by 36 plus 7 is, 35, and plus 1 is 36 in the numerator. And again, which you see is these things also add up to 1. So it's all looking good so far. Okay, so again, I will represent this on the transition graph. Okay, now let's talk about state 12. So state 12, the first element is probability of reaching starting state from 12. That is basically you're saying, can you reach a starting state from 12? Well, if you're in 12, you're here, you've already won. It's an absorption state. So probability of reaching any other state from this 12 is not even a question, because once you reach 12, you're going nowhere. So all the probability is going to be 0 except for staying in 12. So 0, 0, 1, 0. Okay. Similarly for 7, 7. If you're in 7, 7, B has 1. So you can't go anywhere except for staying in 7, 7. So this is very easy that way. And you see now transition graph is fully covered as well. Okay. Well, this was half of the problem done. Now let's do the main equation part. Okay. So I'm just going to add a new page here. All right, so what are we saying? The question asks us, what is the probability A wins? Okay, now let's try to model this in Markov, in the Markovian world. And you understand that A wins when we reach state 12, okay? And it's an absorption state. So I'm just going to quickly make some few notes here. What are the absorption states? The absorption states here are, I think they're absorbing state. I've been calling them absorption for some reason. It's absorbing states. So these are absorbing states. So there are two absorbing states here. One is state 12 and the second one is state 7, 7. Okay, and here A wins, here B wins. All right, so we care about A winning. So our subject is A, right? And the subject state we have, our target state. We talked about target state and absorptions and equations for absorptions. So here it comes. So our target state is 12, okay? So now we're gonna write equations for probability of getting absorption with respect to our target state, our target absorbing state being 12, okay? So if you remember these equations, what we had is we had AI as a probability of getting absorbed in state 12 while starting from state I. Okay, so what it means is basically if you're in state I, what is the probability that you get absorbed in state 12, right? And again, state I has to be one of the state spaces. So it can be a starting state S, it can be state 7, it can be 12, it can be 7, 7. These are all possible states we have, right? So let's do first absorbing states. Okay. So for absorbing states, A12 basically means what's the probability you get absorbed in 12 if you're in 12. Well, if you're in 12, you're already in 12, so it's going to be 1. You're already there. You can't go anywhere, right? If you are in 7, 7, can you get absorbed in 12? No. It's another absorbing state, and you can also see this from transition graph. If you're here, you can't get out anywhere, right? So you can't get absorbed here. If you're in 12, you're going to be here, right? So the probability you get absorbed in 12, if you're in 7, 7, is going to be 0. Again, the reason is this definition here says probability of getting absorbed in state 12. This is our target state. Okay, if you're starting from state I. Okay, now in this is the absorbing Markov chain. Why? You have first of all 2 absorbing states. So the first condition was greater than 1 absorbing states, right? This is already satisfied. Second is all the other states should be able to access these absorbing states. So S can access these absorbing states, right? At least one of the absorbing states, and 7 can also access the absorbing state. Here, right? So it's all good here. Okay, so assumptions are met. Okay, now let's talk about transient states. So transient states, if you see, so these are two transient states. One is S and the second one is 7. Okay. So let's talk about transient state 7. So 7, what is the probability of getting absorbed if you're in 7? This is going to be equal to, again, we're referring to the equations from the last lecture on Markov chains, which talks about the probability of getting absorbed, right? Okay, so this is, the probability of getting absorbed in 12, starting in state 7, is basically you just parse over all the possible states. I'm just going to write it like this. This basically means you go over all possible states in the state space, and here the state space is covering basically S, 7, 12, 7, 7. Okay, so from 7 you can go to any of these states, and whenever you go, let's say you go to state I, so we say first of all, what's the probability jumps to state I? So from 7 you jump to state I, and then you also multiply this with AI, which is probably getting absorbed if you have reached state I. So what I'm saying is basically from 7 you can reach S, you can reach 7, you can reach 12, you can reach 7, 7, right? We're gonna do all possible states, right? And then we basically say, okay, let's say if you jump in any of the states, what is the probability of getting absorbed from that state? Okay, so if we first of all capture the probability of reaching the state, and then we capture the probability of getting absorbed from the state. So if you do this equation, just expand this equation, this will become equal to A7 is equal to AS times probability of 7S plus A7 times probability of 7, 7 plus A12 times probability of 7, 12 plus A7, 7 times probability of 7, 7, 7. Okay, let me just quickly explain what I did. So again, this is simply writing this expression saying from state 7 you, let's say, went to state S. So what is the probability you jump to state S? And then what is the probability of getting absorbed from the state S? Because we care about getting absorbed in, we care about getting absorbed in state 12. So we first compute what's the probability of reaching the state S, and then we multiply it with the probability of getting absorbed in state 12 from this point, from the state S. Similarly, probability of reaching state 7. You're in 7, what's probability you will stay here? And if you stay, what's the probability of getting absorbed in state 12 from this state? This one, we basically go from 7 to 12. We capture this jump of this probability, and then we also capture what's the probability of getting absorbed in 12 if you're in 12. And similarly for 7, 7. So now if you see what's going to be happening is, this is already 0. This is again from transition matrix. You can see easily that 7, 7 is 0. It's right here, right? So 7, 7 is 0. Probability of reaching so we have to use this one because this is our starting point, and we can jump to one of these possible states, right? So I'm just going to use these values, and again, this is going to be equal to, so 29 by 36 times AS plus, you can be in state 7, so it's 0. To reach 12, it's 1 over 36 times 1, because if you're in 12, it's going to be you shall be absorbed, and this is what we've done here. So A12 is equal to 1. So like here, so A12, I just put it here. So this is times probability of reaching 12. State 12 from 7 is again 1 by 36. You can refer it to here. So from 7, you got to reach 12, so it's 1 by 36. And from 7, you reach 7, it's 6 by 36. So now you do basically A7, 7. But again, here it's 0. You can't get absorbed in state 12 after you reach 7, 7. So you don't even have to bother about this probability because this is 0 right here. And again, the reason is pretty clear because B is already 1 in this case. So this is, I can just omit this. Okay, so the equation becomes A7 is equal to 29 by 36 AS plus 1 over 36. Okay, so this is the first equation. Similarly, for second transit state, we write the second equation, which is AS equals to sigma AI times probability of SI, right? If you expand this, this becomes equal to AS times probability of SS plus A7 times probability of S7 plus A12 times probability of S12 plus A77 times probability of S77. This is anyway 0. You can get rid of this last term. Then probability of A, okay, so this becomes equal to AS times probability of staying in the same transient state. So in this case, we're going to be using this row here. Okay, so from S, if you have to stay in S, this is 29 by 36. From S, you have to stay in 7, it's 6 by 36. S, you got to stay in 12, it's 1 by 36. Okay. Okay. All right, so S, stay in S is 29 by 36 plus A7 times probability of reaching 7 is 1 over 30, 6 by 36. 6 by 36 plus of reaching 12. And if you reach 12, the probability of reaching 12 is 1 over 36, but to get absorbed in 12, it's going to be 1, because if you're in 12, you're going to be absorbed there, and it's also mentioned here. Okay, so let's see finally what this equation becomes. This is equal to AS, 29 by 36, AS plus 6 by 36, A7 plus 1 over 36, okay? And I can just put this here. This becomes 7 AS by 36 equal to 6 by 36. I use equation 1 here, which I've computed for A7, and replace it downstairs and replace it here. So 6 by 36, A7 is just 29 by 36, AS plus 1 over 36 plus 1 by 36. Okay, this becomes equal to 7 AS by 36 is 29 to 6 by 36 square AS plus 6 over 36 square plus 1 over 36. Okay, now you can just bring this here. Okay, if we solve further, what we get is, let's do some speed maths. 7 to 42. 252 minus 196, 174. 252 minus 174 is what? 8, 7, 78. 42 by 78. 760. So we get our final answer here. So what this tells us is, if we solve for this is probability of getting absorbed. This is probability of getting absorbed in state 12 when we start, when we are at that starting stage. When we are at starting stage. That is basically what AS is telling us. Okay. And if you look about this more closely, this is what we really want, because we are saying the game is yet to start, and the question asks us what's the probability we're going to win, or at least A is going to win, right? So if we are here and we can compute the probability of getting absorbed from this A starting stage S, then we can practically compute what the question is asking us. What's the probability A wins? Because if you get absorbed in state 12, A wins. So if we can compute what's the probability of getting absorbed in state 12, when you're starting at state S, or the starting state, that's the answer. And this is what you compute here. The two transient states, which we saw here, S and 7. We computed A7 and AS equations, and we solved for AS, and this is what we get. So this is a probability we get absorbed in state A, in AS, or sorry, this is a probability we get absorbed in state 12, starting with stage S. Okay, and this is 1 by 30. Okay. All right, so I hope you enjoyed this video, and if you did, please give it a like, and also subscribe to my channel if you've not so far. And also, if you could share it amongst other people who may be interested in this kind of content, that would be highly appreciated. And also, to let me know what you thought about this video in the comments. All right, till then, see you next time.